So, a geometric mean is the number that holds the means position in a proportion between two other values. So the geometric mean between A and B let me try writing A and B. Would be the number that's in the means position between A and B. If we want to work with x, then x is the geometric mean between A and B, and it would be written like this. Notice, in a proportion, these two positions are the means position, and these two positions are the extremes positions. So here, x is the geometric mean between A and B. In a proportion written in fraction form, we have A is to x as x is to B. And when we cross multiply, or use the means extremes property to help us find the value of x, we end up with x squared equals A times B. Which means we'd have to take a square root to solve for x. So we get x equals the square root of A times B. To solve a proportion for a variable, you have to cross multiply. So when we cross multiply to solve for x, we get x squared equals A times B. That's why we did the means extremes property. Now, here is an example problem with the geometric mean. They might say, find the geometric mean between, we'll say, 3 and 9. And I need to move this down. It's running out of room. Now I know that that geometric mean will be in the means position between 3 and 9. So in a proportion it will be 3 is to x as x is to 9. Or in fraction form, just calling your attention, 3 is to x as x is to 9. Notice how in fraction form the means position is lower left, upper right. So when we solve this to find the geometric mean between 3 and 9, we will cross multiply, giving us x squared equals 27. Now we have to take a square root to find the geometric mean. So we're going to have x equals, and generally when you do a square root you think positive or negative, but in geometry you can just stick with the positive case, because we're working with lengths or area, and those are measured in positive values. So when we do this square root, we're just thinking square root of 27, not necessarily plus or minus square root of 27. We can stick with that. Now, when we do the square root of 27, we have to look at the factor tree for 27. 27 is 3 times 9, which is 3 times 3, and I see that I have a repeated factor of 3. So I can simplify the square root of 7 by putting those factors together as a square root of a 9 times the square root of the number that's left, square root of 3. I know square root of 9 is 3, so I write x equals 3 times the square root of 3. And that's where I leave my answer. 3 root 3 then is the geometric mean between 3 and 9. It's the number that would hold the means position in this proportion between 3 and 9. Now, using the geometric mean then in Theorem 8.1. Theorem 8.1's corollaries work with the geometric mean. Theorem 8.1 is just about similar triangles. So Theorem 8.1 says the altitude, if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. Now when I draw a right triangle, and then I draw an altitude to the hypotenuse, the altitude is going to come through the right angle and be perpendicular to the hypotenuse. So the altitude is going to come, and I don't think I drew it very perpendicular, so I'm going to rotate it until it looks perpendicular to me. You guys can see better because you're farther away. Does that look perpendicular? Yeah, close. Okay, close. Now when we label this triangle, generally you will label the right angle vertex a C. That's generally the way you do things. And then the side that's opposite angle A here is called A. And the side that's opposite angle B here is called B. And then the hypotenuse is usually called C. So you have, according to Pythagorean theorem, A squared plus B squared is C squared, which is a common type formula, okay? So this hypotenuse is called C, like so. And of course we have these other pieces of the other triangles. But meanwhile, our goal is to try to prove that these triangles are similar to each other. We'll call this point right here by E, by angle, angle, yes. So our given information is basically the diagram. I'll leave it that. And what we want to prove is that we have similar triangles. So the tricky part about this is getting the right corresponding orders in the right place. So how I look at these triangles is I think, okay, in this original triangle, I have a hypotenuse AB, I have a short leg AC, and I have a long leg BC. So when I name this triangle ABC, I am naming it, first off, hypotenuse, then long leg as I walk around the triangle from A to B to C, right? Which means when I look at the other two triangles, I have to think hypotenuse, long leg, and then walk around the triangle in the order I would have to go in order to go from hypotenuse to long leg. So this triangle here, which is drawn in green now, if I go hypotenuse, long leg, I would go triangle ACE. So similar to triangle ACE, which is similar to triangle, and now I have to look at the other triangle. Let's outline it in blue. We have hypotenuse, long leg, so it would be triangle CBE. Now, first off, these two triangles are similar to the original triangle by angle. How? Well, triangle ACE has angle A, and so does the original triangle. So by reflexive, angle A is congruent to itself, and they both have a right angle. Secondly, triangle CBE has angle B, as does the original right triangle, and they both have a right angle. So each of the original triangles, each of the smaller triangles, share an angle with the original triangle, and all of them have a right angle. So by angle, these triangles are going to be similar to each other. Which means I can say that each of these is similar to triangle ABC. So triangle ACE is similar to triangle ABC, and triangle CBE is similar to triangle ABC. Since they're both similar to ABC, they're going to be similar to each other by a transitive type property. If they are both similar to the same triangle, they will be similar to each other. So triangle ACE is also similar to triangle CBE. If triangles are similar, all their angles are congruent, so by transitive property, all the angles of these two triangles will also be congruent. So we'll say by a transitive property. We have two corollaries now that follow this, that use the fact that these triangles are similar. Corollary 1. Corollary 1 says, when the altitude is drawn to the hypotenuse of a right triangle, the length of the altitude is the geometric mean between the segments of the hypotenuse. segments of the hypotenuse. So again, we need that picture drawn where we have a right triangle and we have an altitude drawn to the hypotenuse. And what we are going to have are side lengths, since this is A, B, and C. We're going to have a side length A, side length B, a side length C, which is this whole hypotenuse, a side length D and E, which begin at that point right there, and a side length F, which is the length of the altitude. So our given is this diagram here. And what we want to prove is that the length of the altitude, which is F, is a geometric mean between the segments of the hypotenuse. So geometric mean between D and E. We want to prove here is D and E, and F has to be in the means position. We talked about how the means position is lower left and upper right. So F is the geometric mean between D and E. That's what we're going to prove. We're going to do this by similar triangles. Since triangles are similar, all their corresponding sides are in proportion. So I could say, if I'm looking at these two triangles here, D and F are both on the smallest triangle. Nick, just waking you up. And if I look at F and E are both on this other part of the original triangle, right? So D and F are the short leg and the long leg of the smallest triangle. F and E are the short leg and the long leg of the other half of the original triangle. We have short leg is to long leg then. On both triangles will equal both smaller triangles will equal and so we have D to F. Let me write it in a different color. D to F as short leg to long leg, F to E. Again, to help you see it better, let me erase this F and try again on it. But to help you see it better, let me outline this triangle green. D to F is short leg to long leg. Let me outline this triangle red. And F to E is short leg to long leg. So we're going short leg to long leg in each of those two triangles. That means since the triangles are similar, that we have a proportion, and that's what we want to prove. Easier than thinking of similar triangles in short leg and long leg, however, is to remember that this altitude right here is the geometric mean between these two pieces. Much easier than thinking similar triangles. Once you know F is a geometric mean between D and E, you don't have to think short leg, long leg, and confusing two triangles. You can just know that D is to F as F is to E. Okay. Our second corollary, corollary 2 for Theorem 8.1, gives us a couple more geometric mean situations. Corollary 2 says, when the altitude is drawn to the hypotenuse of a right triangle, then each leg is a geometric mean between the hypotenuse, that means the whole hypotenuse, and the segment of the hypotenuse that's adjacent to that leg. Okay, so here's our right triangle. We need an altitude drawn to the hypotenuse. And we're going to again label our triangle so that it has sides A, B, and C. And then we have shorter segments E and F. I did it different, that's okay, I guess. Maybe I should be consistent, I don't know. Should I? Okay. So this is D and E and F. So our given again is our diagram. And what we want to prove is that each of the legs, now the legs are B and A. But let's focus on B to begin with. We want to prove that B is a geometric mean between the whole hypotenuse. What is the whole hypotenuse? No, Dustin and Branson, that's not okay. I want your attention. B is a geometric mean between the whole hypotenuse. What is the whole hypotenuse? C. So between the whole hypotenuse and the piece of the hypotenuse adjacent to B. What's the piece of the hypotenuse adjacent to B? D. So B is a geometric mean between C and D, which means in a proportion, B has to have the means position. Means position is lower left, upper right. And it's a geometric mean between D and C. Between D and C. The second thing we're proving, let's focus on A now. A is the other leg. A is a geometric mean between the whole hypotenuse and the piece that's adjacent to it. So A is a geometric mean between the whole hypotenuse And what's the piece of the hypotenuse adjacent to A? Which means, in a proportion, A will be in the means position between the whole hypotenuse, Tommy and Bart, and the piece adjacent to it. It's C and A and E. Now, again, the reason why these two geometric mean situations are true is because the triangles are similar. So, let's think about this first one. D is to B as B is to C. D and B are both in the smallest of the three right triangles. B and C are both in the original right triangle. What they are is, think of the smallest right triangle here, Dustin. We have short leg to hypotenuse when we go D to B. So we have short leg is to hypotenuse. And in my smallest right triangle, that would be D to B. And in the original right triangle, short leg to hypotenuse, would be B to C. Now thinking about the red situation there, C to A is A to E. The red is on this other half of that original right triangle. So A and E are hypotenuse and long leg. And that would be A to E. I should move that over because that actually ends up being the second piece to this proportion. If we look at the original right triangle, the red is also C and A, hypotenuse and long leg of the original right triangle. So, Bar, I don't think you can sit over there.
Yeah, the first part.
Because you're talking. Again. So I'm going to put you where Mark is, then you don't have anyone around you, and that way Mark can have a seat back.
Mark will look at you about it's small.
Technically, I usually don't say there's assigned seats, but if I need to, then that happens. Okay, so now, hypotenuse to long leg would be C to A for the original right triangle, and for the red, smaller right triangle, it is A to E. These two are both true because the triangles are similar. And when triangles are similar, their corresponding sides are in proportion. Alright, the whole geometric mean idea with this specific triangle can be kind of confusing because there's a lot of pieces there. So what I like to do is I like to think of this triangle as a duck foot. It's a webbed foot. A duck has a foot that looks something like this, right? C is where it joins to the leg. And then from there we have besides B, F, and A that are the bones in the duck foot. Okay? D, E, and C are all part of the web of the duck foot. So in your duck foot here, the pieces that are the geometric mean are always the bones. B is a geometric mean between D and C. F is a geometric mean between D and E. A is a geometric mean between E and C. So the bones are always the means, and the webbing of the foot are always those values that they're a mean between. Okay? So when I draw a brand new diagram where we can't see any of that information, so first I'm going to keep the orientation exactly the same as what we had before. When we put that altitude in there, try to make it a right angle again. And I have side lengths A, B, D, E, C, and F. And I want to fill a proportion out for each of these geometric mean situations. First thing I'm going to ask is, what is the mean's position in the proportion? The bottom here, the top here, bottom left, top right. So these are the mean's position in each of these proportions. Now, which of these segments in this duck foot are the means? The bones. The bones are the means. So B, F, and A are the means. So B goes in the means position, as does F and A.
Weird.
Now, picking on B, because it's the first. What is B the mean between? Now you're thinking pieces of the webbing, right? B is the mean between D and C. The piece of the hypotenuse adjacent to it and the whole hypotenuse. Notice both of those pieces intersect B at that point. D and C. C actually is this segment right here, and it intersects B at that point, just like D does. Okay? Now, F is a geometric mean between two segments. What is F the geometric mean between? D and E. Notice both of those segments intersect F at that point. So F is a geometric mean between D and E. Now, what is A the geometric mean between? C and E. Notice both of them intersect A at that point. Okay. What I'm going to do is take this triangle, rotate it around, and give those values different names. And see if we still understand what this is. You ready for it? Okay. Triangle. Rotate it around. Altitude drawn to the hypotenuse. different names for all these pieces. P, Q, R, S, T, U. Okay, my question is, I know I have 3 geometric means, and I'm going to ask Branson to come up and circle the means position in each of these geometric means. The next thing I'm going to ask one of you is, what are the geometric means? What are the 3 values that go into the means position that Branson is correctly identified? You can't. So I'm going to ask one of you that question. What are the 3 geometric means? What are the 3 values that go into these positions that Branson has correctly identified? So Hannah, come on up. What are the 3 geometric means? P is correct. Q is correct. U is correct. Because the means are the bones. This time my duck foot's going up this way, right? The means are the bones. Okay? So P, U, and Q are the bones here. Now my webbing, oops, let me try doing a webbing. My webbing does something like that, right? And the whole foot, you might say. Okay. So now, as I do the mean, the other values that P is a mean between, my next question for each of you, for each of these proportions, what are they the mean between? I'll pick on a different person each time. So, first off, Nick, what is P the mean between? Can you answer that? Okay, so who thinks they can answer that? Because if you're paying attention, you can. Tommy, can you answer that? P is the mean between S and T. That is correct. Notice P comes down and hits the web right there, right? What are the 2 segments that hit the web right there? S and T, right? Okay, now, using that idea, what is Q the mean between? Jessica, can you answer that? R and T is correct. Because, think about it, here we have Q coming down, hitting at this point. The 2 pieces of the web that hit at that point are R and T. So Dustin, I think, has already helped me. So we have now, what is U the geometric mean between? And can you answer it, Kira? R and S is correct. R and S. Because U comes down and hits the webbing right there. And the 2 other pieces of the web that hit right there are R and S. Okay.